Okay, so I'm sharing my screen. Let me know if it is visible. Okay. Is my screen is visible? Is my screen is visible? Okay. Okay. So I'll start. Okay. Students, 18. Please ask everyone to join the class. Already used to start bit late. You should be guys should be ready by that. Okay, I'll start the class. So I have made a video deflection of beam. I have shared in the group also. If you have gone through, then you will understand clearly. So next our topic will be deflection of beam. I have discussed the introduction part and one derivation in my video, but today I'll discuss once again because that was I think you have not gone through that video. Okay, so I'll continue with that again. So basically deflection of beam. What is deflection of beam? So the word says this is your simply supported beam, right? It is has been loaded. This beam has been loaded. So when it will load it when a load will come to a beam, it will deflect, right? But in your general structure, the beam should not be deflected. This beam should be able to carry this load. But what is the if the load is exceed the carrying capacity of this beam, so this beam will deflect, right? So this deflection you have to find out what is the deflection in that beam, and you have to check that this deflection in when you design a beam, you have to check that this deflection is in within permissible limit. The main thing is that this deflection shouldn't be in your beam, okay? But if the deflection is coming, then that deflection should be within permissible limit. So this deflection is also known as elastic curve, okay? This x is the distance where you're getting the deflection. This is the whole length. Suppose this the beam is of 6 meter length, and you're getting a deflection of y at, suppose you need to find the deflection at 3 meter distance. X can be 1 2 3, any distance, 0.5 meter, any. So you need to find the deflection at x. So what will be the deflection? Generally deflection is represented by y, okay? So, if I see with the definition, it is the vertical distance of the beam measured before and after loading. So, before the loading, the y will be 0, and after the loading, this there will be some value of y. Okay, deflection at the support is always 0. The deflection, if you see, there is no deflection at the support because these points are hinged. This has been given a hinge support, so there is no. Always remember, if someone asks you in the exam or MCQ comes in your competitive exam, that what will be the deflection at the support, so it will be automatic. Don't get confused. Deflection at the support is always 0, okay? Now there will be one more word. So deflection is measured from the original neutral axis of the deformed beam. This is the original neutral axis, okay? It is measured from the original neutral axis to the neutral axis of the deformed beam. So this is the neutral axis of the original beam, and this is the neutral axis of the deformed beam. So the distance between the neutral axis of the original beam and the deformed beam is your deflection. The displacement y is defined as the deflection of the beam. It may be necessary to determine the deflection y for every value of x. As I have discussed, you need to find the deflection at 1, x is equal to 1, x is equal to 5, any value along the beam. The relation may be written in the form of an equation, which is frequently called the equation of deflection curve. So we'll see an equation for this curve. This curve will have an equation, which is also known as the equation of the deflection curve, or this curve is also known as elastic curve of the beam. Now, what is the importance of beam deflection? A designer should be able to determine deflection, that is in building codes. This is the criteria. You have been gone through, I guess, one IS 1456 for the design purposes. Very important IS code you will require in your whole life if you remain in this field, in design field. So this is building code says that your deflection should be L beam by 300. This is the formula given by the IS code, that your deflection should be less than your L beam, means length of the beam divided by 300. What is the length of the beam? Suppose you have been given length of the beam as 8 meter. So 8 meter divided by 300. So your deflection should be less than that value. Analyzing statically indeterminate beams involves the use of deformation relationship. So I have discussed what is statically indeterminate and what is statically determinate. So statically determinate beams will be those beams where you can use those three equations of motion to find the reactions. Okay, those will be considered as statically determinate. And statically indeterminate, where the reactions are insufficient to find those reactions. So analyzing statically indeterminate beams involves the use of various deformation relationships. So now, what are the methods of determining beam deflection? There are various methods. Okay, double integration method, moment area method, elastic energy method, method of singularity functions. There are many methods. Okay, so we'll discuss two methods only here. So let's start with the double integration method. So the deflection curve of the beam is this. So I said this is, let me go back to this. So this curve, I am I my cursor is moving. You are able to see my cursor. You are able to see my cursor. Please respond. I'm moving my cursor. Is my cursor is movable? You are able to see my cursor. Hello.
Yes, ma'am.
Okay. Okay. Then fine. So this is the equation. Okay. Uh, Please go through my video I have shared. Okay. So you will understand what I'm saying. So this is the you have to derive this equation by yourself. Try. Okay. Take it as assignment. I've given the assignment into that video. I've said that this will be your assignment. So go through that video once. So this curve has an equation which is, this is the equation. So the deflection curve of the beam is this. This is the equation. This equation is called as deflection curve equation. So this is the equation we'll use to determine the deflection of various beams, cantilever beam, simply supported beam, for different loading conditions. In order to obtain y, above equation needs to be integrated twice. So to obtain the deflection, you need to integrate this equation twice. Why? Let me note. I'm taking yellow color. Okay. So when you see what is d square by, let me take another color. Okay. D square y by d x square, right? When you integrate this one, this will become what? Dy by dx, right? When you integrate this one, this will become y. So y is our deflection. So you need to integrate once and twice. You need to integrate twice to get the deflection in order to obtain y. Y is what? Our deflection. So above equations needs to be integrated twice to get the deflection. This is the equation of beam deflection equation. This is the equation of deflection curve. This equation is used in all the cases to find out the y value. Okay. And there will be on one word, slope. Let me go back to this. There will be one more term of slope. With deflection, you will get a slope also. And what is slope? It is the angle in radians measured between the tangent to the elastic curve and the original axis of the beam. So if I draw a tangent to this point, okay, so the angle made by this tangent from the original axis. It is the angle in radians measured between the tangent to the elastic curve and the original axis of the beam. This is the original axis. I have drawn a tangent to this beam. So this is your theta. It is saying that at what angle this deflection curve is moving. Suppose I am drawing a tangent at this. So the angle between this original axis to this beam will be your theta. Okay, this will be the theta. When you come to the middle part, there will be no angle, right? There will be no angle. So the theta is 0 at the mid span. So where the deflection is maximum, your theta will be 0 because it is not making an angle. Let me erase this part. So if I draw a tangent to this elastic curve, sorry, this was not the angle, this was the angle. This is the slope. This is the slope. But when I draw a tangent to the middle part, there is no angle, right? So your and at see, if you see the deflection at this part, the deflection will be less at this part, right? Some students are in the waiting lobby. Let me add them. Okay. Okay. So this is your theta. Okay, this is your theta, and this is your theta value, and this one is your deflection. So see, deflection at this part is very less, right? Deflection at this part is the maximum. At the mid, if you see the mid span, deflection is maximum. So at the mid span, your deflection will be maximum and your slope will be 0. But at support, your deflection will be 0, but you will have some theta. So at supports you will have slope, but deflection will be 0. And at mid span, deflection will be maximum, but your slope will be 0. These are some boundary conditions we will see. So slope is what? It is the angle in radians measured between the tangent to the elastic curve and the original axis of the beam, and it is denoted by your theta. Okay, or dy by dx, or you can write dy by dx as hy dash. And our deflection is generally represented by triangle or d square y by dx, or you can say y. Okay, triangle, your deflection is represented by y, d square by dx square, or y double dash. Okay, what is the meaning of y triple dash? It will be d cube by y dx cube. Okay, y double dash is d square y by dx square, y dash is dy by dx, y cube is d cube y by dx cube. So our theta is your dy by dx, y dash. Our deflection is d square y by dx square, y double dash. So why I have discussed this one? Because if you see this one, if I integrate this one, if I integrate d square by dx square by once, I'll get theta, right? D square y by dx square. If I integrate once, I'll get dy by dx. And what is dy by dx? It is our theta. Again, if I integrate this one, I'll get y, which is our deflection. Okay, so just be clear about this. In order to obtain y, above equation needs to be integrated twice. So this equation needs to be integrated twice to get the deflection, and this equation needs to be integrated once to get the slope. Now m is equal to, we have discussed, we have bending equations, right? So this is from bending equation only. So movement is your E by I by rho, and 1 by R is equals to m by EI is equal to K. They have represented the curvature as K here. In the earlier classes, I have represented curvature as R. So no issue with that. And an expression for the curvature at any point along the curve representing the deformed beam is readily available from differential calculuses. The exact formula of the curvature is this one. So what is the curvature of this beam? This K is also represented by R. In many books, they have represented this curvature by R and some K. So don't get confused. This curvature is same. It has formula d square y by dx square 1 plus dy. This is the formula. dy by dx is very small. So this part will be eliminated. So your curvature is nothing but d square y by dx square. So this is the equations for this beam. They have derived this equation basically in small, in very concise manner. So please go through the derivation of this equation. I'll suggest some books, or you can go through some YouTube channels also how to derive this equation. So please go through the derivation. Okay, the derivation of this deflection equation, or submit as assignment uh, by the end of this month. Okay, by the end of this month, you first understand how the derivation has been done, each and every step, then do by yourself. That will be a practice for you. So submit at the end of this month. No issue. So next, the integrated procedure. The integrated ones yields to slope. As I've discussed, if you integrated that equation once, you'll get a slope which is dy by dx at any point in the beam. Then integrating twice yields to deflection y for any value of x. The same thing I have discussed. If you integrate this equation, if this is the bending equation, remember ei d square y by dx square equals to m, and this equations has been partially derived from the bending equations we have discussed earlier. Okay, so if you integrate this one by once, you will get slope at any point in the beam, and if you integrate twice, you will get deflection at any value of x. The bending moment must be expressed as a function of the coordinate x before the integration. So what bending moment should be expressed in terms of x before the integration. Differential equation is second order. The solution must contain two constants of integration. So this is the basic part of your math. When you integrate your differential equation, you get two constants. Okay, they must be evaluated at excuse me, just give me a minute. Okay. Am I audible? Hope I'm audible. Please stop me if I'm not audible and screen is not visible. Okay. So integrating once yields to slope dy by dx at any point in the beam, and integrating twice yields to deflection y for any value of x. So, okay, I was here, right? So, differential equation is second order. The solution must contain two constants of integration. So, when you integrate once, you get one constant. So, when you integrate twice, you will get two constants. So, they must be evaluated at known deflection and slope points. At a simple support, deflection is zero. At a built-in support, both slope and deflections are zero. So, this line says that when you integrate, you need to evaluate those constants also. Let's see. Now, what is the sign convention? This is your positive bending. They have considered this one as positive bending and this one as negative bending. What are the assumptions and limitations? Deflection caused by shearing action negligibly small compared to bending. So in deflection of beams, we have not considered any shearing part because this is which is very negligible in amount. So we have considered the pure bending case. Deflections are small compared to the cross-sectional dimension of the beam. These deflections are very small compared to the cross-sectional dimension. Suppose your beam has size of 400 mm by 300 mm and it is 9 meter long. So the deflections are very small, okay, compared to the cross-sectional area. And if you get a large deflection, then you will be out of your job. The boss will throw you out. This deflection should be, you have to design those beams in such a way that you will get a very minimum deflection. At all proportions of the beam are acting in the elastic range. So so whatever the bending deflection is coming, it is coming in the elastic region. And what is elastic region? See, every topic of the classes are related, right? Now, if you ask me what is elastic region, I won't go back. You remember, I guess, what is elastic region. This elastic region refers to the your stress strain path. So the region where when you apply a load to a beam or a structure, it will come back to its original position, right? Beyond this region, your beam or structure will not come back to this region. So what are the all proportions of the beam are acting in the elastic region. So throughout the beam is acting as an elastic range. Whatever you apply a load, it will deflect, but when you remove the load, it will come back to its original position. Okay. Now you can say that it is not possible in the day-to-day life, right? It is possible. Beam is straight prior to the application of load. So we are assuming that your beam is straight when before the application of load. So I'll take an example of cantilever beam. This is the cantilever beam fixed at one support. The length is L. This is why it is drawn in X and Y coordinate. Now when I have applied a load, it gets deflected. I have applied a load at the free end. Okay, this is my free end. I have applied a load at the free end and the beam has deflected in this direction. So to counterbalance this load, there will be, always I have discussed, there will be one force also and one moment also at the this part, right? So what will be the force? P, and the moment will be M, which is also represented as P into L. So if I take a section XXX at this, if you use your equations of motions, you will get the equations like this: M is equal to minus P into L. Why minus P into L? It is in anti-clockwise direction, plus Px. This is in anti-clockwise direction. This P will be P into X will be your clockwise direction. So this is my moment equation. This is also a moment equation. So this was the moment equations from the beam. Okay, this is the moment equations. I'll not discuss how I get this, because we have discussed this one in the shear force and bending moment class, right? So this is the moment equation. So this one also I have the equation of moment for deflection of beam is this one. So I'll replace this M by this minus PL plus PX. Now I'll integrate this one. So if I integrate once, I'll get this equation: EI d square y by dx square will become dy by dx equals to, this is the constant part, so constant part will get a x part. This is the x, integration of x will be how much? X square by 2, px square by 2, and there will be a constant of c1. Please stop me if you don't understand at any point of the class. Okay. Now x at x equals to 0. I'm considering at x equals to 0 here and at x equals to L. So at x equals to 0, your dy by d is 0. So this will, you'll get c1 equals to 0. So this is the equation I got. I have integrated this one. I got the c1 as constant. Now I need to find the c1 value at x equals to 0. So at x equals to 0, my c1 is 0. So I have to place this c1 in this equation. Now integrating twice. Now the same equation I'm integrating again. So if I integrate dy by dx, it will become eiy minus, this is x, now x square by 2 minus pl x square by 2. This is x square, right? So it will become x cube by 3. So px cube by 6. 3 into 2, 6 plus c2. Now again I have to find the value of c2 at x equals to 0 at boundary conditions, at x equal to 0 and at y equals to 0. At x equal to 0, my equations will be, I'll get c2 is equal to 0. So place the value of c2 in this equation. I'll get the deflection. I'll get the equation like this. And at x equals to L, at x equals to 0 was here. X equals to 0, let me note. X equals to 0 was here, and then this is your at x equals to L. So at x equals to L, your y will be y max. Now this is the equation. Put the value of here x as x by L square. This x is replaced by L. So PL L square by 2, P L cube by 6. Now I got, this is the equation, P L cube by 6. Now my deflection at this point is PL cube by 3i. So this is the equation. For simply sort of cantilever beam with point load, you will get the maximum deflection of PL cube by 3i. Okay, how? Let me explain this one once again. This is the moment equations for these beams. You have to find out the moment equations for a particular beam given for a given load. Once you have found out the moment equation, you have to equate that moment equations with this equation: Ey d square y by dx square is equal to m. Right? You have to replace this m by the moment equation. You have replaced. Now integrate this once. This is the integration. Find out the value at boundary condition. Boundary condition means at x equals to 0 and there is no load, so no need to find here. Then x equals to 0, x equals to L. So at x equals to 0, you got C1 equals to 0. Again at x equals to 0, you got C2 is equal to 0. So you have found out the equation. Now there is no deflection. See, if you see the figure, there is no deflection at this point. Now you have to need to find the deflection at this point. So this is the general equation. This is the general equation. Suppose you have been asked to find the deflection at L by 2. That means at midpoint. So replace this x by L by 2. Okay. This is the general equation. This is the y. This equation is giving y maximum. What will be the maximum deflection? But if you need to find the deflection at this position, so first find out what is the distance of this. So replace this x by this distance. Suppose you have been asked to find the deflection at L by 2. So replace this x as L by 2. You'll get a different equation. Suppose you have been asked to find out the deflection at L by 3. So replace this x by L by 3, you will get a deflection. Okay, understood. Now they have put x equals to L. That means x equals to L where the deflection is maximum. So the maximum deflection in a cantilever beam with point load at the free end will be PL cube by 3EI. Understood? Any confusion in this part? Please respond. Any confusion in this part? Please reply so that I can. Am I audible? Am I audible? Hello.
Yes, ma'am.
So screen is understood this position, this one. Cantilever beam with simply supported load. What is the deflection equation and how to find the maximum deflection?
Ma'am,
Yeah,
can you remind me how to apply boundary question? I forgot.
moment equations. I have discussed now.
Boundary.
Boundary will be like this one. See, boundaries at x equals to 0 and at x equals to L. That is the boundary condition. You have suppose I have been given a load. Suppose there is a, just wait a minute. Okay. So suppose at this equation there will be one load. So at x equals to, this is the load at L by 2. So your boundary condition will be x equals to 0, x equals to L by 2 and at x equals to complete L. So these are called as the boundary conditions. Suppose I have been given one more load. Let me draw this one, remove this one. Suppose there is two load. Okay, there is two load. This one load is at L by 3. Again this one is load at L by 3. So your boundary condition will be at x equals to 0, at x equals to L by 3 and at x equals to, this is suppose 2L by 3 and your x will be L. So there will be different boundary conditions. Okay, now there is no load, only load at the end point, so boundary condition 2 will be sufficient at x equals to 0 and at x equals to L. Clear this part?
Ma'am,
Yeah.
when we put x equal to 0, we are getting dy by dx equal to 0. So are we putting this x equal to 0 in any equation? How do we get dy
Yeah.
by dx?
No. How you got dy by dx equals to 0?
Yeah.
No. He is saying at x equals to 0, there is dy by dx means your slope. The slope is 0 no, at this point. Dy by dx, wait. Where is, You are asking me this one. This one. You are asking me this one.
Yes, yes,
You are asking me why dy by
yes,
x equals to 0, right?
yes, yes.
At x equals to this, at this position, your x will be 0. So this, the whole term will become 0, na? At x equals to 0, so the term will become 0. You can, there is no place for integrating x. See, at x equals to 0, your dy by dx term will definitely will become 0. There is no x. X equals to 0 means there is no position of L, right? Understood? Uh, Go through my video. I have made the self-made video, na? Go through once. Then it will be more clear. I have discussed there in another way. Please go through that video also. At x equals to 0, your deflection is 0. If you see your deflection at this, at x equal to, there is no point of x, so it becomes 0. So that's how you need to find the C1 value. Okay. And again at x equals to 0, at x equals to 0, at this position, your y's deflection is 0. This is the boundary condition. So clear? Any confusion? So I'll move to the next one. Now cantilever beam. Now cantilever beam with UDL. So this is the equations for your cantilever beam with UDL. Okay. This is the moment equations. First, you have to clear how to find those moment equations. What they have done, they have taken a section. Okay. Uh, this part was discussed. First, you have to clear with shear force and bending moment diagram in different beams. So how to find the moment in cantilever beam with UDL, you have to clear with that. So once you get the moment equation, replace this moment equations with Ey d square y dx square by m. So replace this m by this moment equation. Then you integrate Ey dy by dx. This the L minus x square. So it will become cube by 3 plus C1. Now at this position, x equals to 0, dy by dx will be 0. So place the value here and you will get the C1 VL cube minus 6. So place the value of C1 is equal to this. So this is your equations for slope. So if you need to, this is the equations for your slope. So if you need to, if they ask you find the slope at x equals to 3 meter. So replace this x by 3 meter, you will get the slope at that point. Okay. When you integrate twice, you'll get this equation, put the boundary conditions, then you'll get a moment equations also. Now you can find the moment at, you can find the deflection at any point of the x by this, replacing this one. Okay. Now maximum occurs at x equals to L. So this will be the maximum equation, maximum deflection for cantilever beam with UDL. Now this is for simply supported beam with UDL. Okay, this is a simply support beam with the UDL. I'm taking a distance of x and I have founded the moment equation. This is my moment equation, right? We have for a simply supported beam with UDL. This is the moment equation. So I've replaced this moment equation you will able to find from shear force and bending moment diagram, right? Don't need to draw the diagram. Equations will be sufficient. Sorry. So replace that moment with deflection equation. This one. Then integrate this one once. You'll get this equation. Since the beam is symmetric, x equals to L by 2. Now this is the symmetric beam, right? So your x is equals at x equals to L by 2. That means at this distance, your slope is 0. dy by dx is 0. So put the value of this one. You'll find the C1 value. So place the C1 in this equation. You'll get equation. So this is the slope equation. You can find the slope at any point of the x by this equation. Now integrating again, I'll get this equation. Now find out the value of C2 with this boundary conditions, x equals to 0, y equals to 0. This is your this is your deflection equation for simply supported beam with UDL. Now replace that x with any distance. Now we know the maximum deflection will occur at L by 2, right? So replace that x is L by 2, that will be your maximum deflection. FWL4 by 384 EI. This EI will come to this. They have replaced the negative to show the magnitude, because this sign represents your direction of the bending moment. Now this is the simply supported beam with point load at the midspan. M equation is P by 2x. So replace this with this, and now this equation is for x equals to for x more than 0 but less than L by 2. For this position, for this part, this is the okay. You can this is the moment equation for this region. Okay. Now so this is the equations for this region. Now integrate this part. Since the beam is symmetric, at x equals to L by 2, your dy by dx will be 0. That is, your slope will be 0 at this position. So I have taken x at x equals to L by 2, dy by dx equals to 0. Okay, you was asking why dy by dx. So this is the slope. So slope, where the slope is 0, take that x equals to that distance only. And take that way also. Find out the C1 value. Put the C1 value in this equation. This is your slope equations for simply supported beam with point load. Okay. Now again integrate. You will get another equation. You will get C2. Place the boundary condition. You will get the value of C2. Replace that C2 value in this equation. You will get the deflection equation. Now you can find out the deflection at any point. The maximum deflection we know for the simply supported beam with point load will be at L by 2. So we have replaced the x by L by 2. So I got the deflection equation as PL cube by 48 EI. Now in the next class we will discuss the moment area method. Okay. Please go through this slides I'll share today. Okay. Write your roll numbers in the chat box, please. Ma'am, while integrating, why we have to put EI in front of? We are not putting EI in front of. That is the equation of deflection curve. EI d square y by dx square equals to m is the deflection equation. First, see the first is you have to first find out the moment equations for a particular beam. Whatever beam is given to you, suppose whatever beam is given to you, okay, like simply supported cantilever beam, or with different loading conditions, point load, UDL. Okay, first you have to find the moment equations at any point, at any section of the beam. Okay, once you find out the moment equations for that beam, you have to equate that moment value with your equation, which is EI d square y by dx square equals to m. So you have to replace that m with your moment equations. Now I got a equation. Now you integrate once, you'll get slope. Integrate twice, you'll get your what, deflection. After integrating once, you will get C1 value. Okay, you have to evaluate that C1 value at boundary conditions. Once you getting the C1 value, place the same value in the first equations, you will get the slope equations. Again integrate that slope equations, you will get another constant C2. Now find out the C2 value at boundary conditions and place the value of C2 in the equations, you will get the deflection equations. Okay, hope clear. Please write, meeting will end soon, so please write your roll numbers in the chat box.